Hi, my name is Chaz Harris. I'm the Vice President of Marketing and Clinical Development for STEM Labs. We've developed these series of blog posts and videos to provide high-level education on key topics in regenerative medicine. As our company has grown, we've built a large knowledge base of information around regenerative medicine topics that we're sharing to help educate clinicians, patients, and others interested in regenerative medicine. In this video, Annalise Roy, one of our scientists, is going to talk about hyaluronic acid. So I'll hand it over to Annalise to take it from here.
Thanks, Chaz. Hello, everyone. Thanks for tuning in. As Chaz mentioned, our topic for today is hyaluronic acid. So what is hyaluronic acid? Hyaluronic acid, which we also call HA, is a type of carbohydrate chain made up of individual disaccharide units called a glycosaminoglycan. It is hydrophilic, meaning it's a water-loving molecule that can bind up to 1,000 times its weight in water, which makes it an important factor in maintaining tissue hydration. HA is also viscoelastic, giving it special physical properties that allow it to resist compression and deformation from stretching. This is why it's considered to be the ideal biological lubricant found in high quantities in synovial tissue. These viscoelastic properties allow it to lubricate and cushion joints. But where is it found in the body? Well, HA is a key component of the extracellular matrix and is synthesized at the cell surface membrane throughout the body. It can be found in the space between your cells, providing a protective coating to surround and protect those cells. The turnover rate of hyaluronic acid in the extracellular matrix is very high, being replaced every 12 hours to 3 days. HA organizes into large matrices of proteoglycans to create a hydrated matrix around cells and tissue throughout the body. On top of its structural properties, HA plays a critical role in tissue maintenance, regulation, and signaling. It helps modulate inflammation, having both pro- and anti-inflammatory properties. The majority of HA signaling depends on the HA molecule itself. HA molecules vary in the length of their disaccharide chains, giving us both a high molecular weight and a low molecular weight HA. As we touched on before, new HA is made by cells at the cell surface. As HA is turned over, enzymes break down long HA chains, which we call high molecular weight HA, into shorter chains, creating a lot of small molecules of HA, which are called low molecular weight HA. Eventually, all of these small chains are going to be broken down and recycled by the body. There is a natural balance between the synthesis and breakdown of hyaluronic acid molecules. When homeostasis becomes unbalanced with too much matrix breakdown, low molecular weight HA will build up. A buildup in low molecular weight HA increases the expression of inflammatory mediators and can lead to chronic inflammation. It also represents a breakdown of the extracellular matrix integrity and a weakening of the molecular protection around cells. While chronic expression of low molecular weight HA is a problem, it's important to remember that an appropriate balance of low molecular weight HA is needed for your body to function correctly. Because of the different signaling roles of high and low molecular weight HA, they are being studied and used as treatment options for different therapeutic applications. Low molecular weight HA is currently being researched for its role in the innate immune system and for its potential benefits in the field of dermatology as a cosmetic filler. On the other hand, researchers and physicians have published extensively on high molecular weight HA treatments for chronic conditions like osteoarthritis, as well as a treatment option for dermatitis and dry eye. High molecular weight HA injections for osteoarthritic knees is a common alternative to steroid treatments and takes advantage of the mechanical, lubricating, and anti-inflammatory properties offered by HA molecules. Research has also been done into HA's role in healthy tissue repair processes. Studies have shown that HA naturally plays a role in each of the 3 major stages of this process. At the onset of a wound, HA helps to provide a framework for blood clots, and it's going to be involved in the mechanism that modulates inflammation and infiltration of cells into the extracellular matrix. HA helps to stimulate inflammatory cytokines to start the critical inflammatory stage of wound repair and will signal the migration of immune cells to the wound site. During the proliferation phase, HA will act as a cellular signal to promote cell growth and the organization of granulation tissue. As we move into the remodeling phase, HA in the wound bed will be broken down, making low molecular weight HA that helps in the creation of new blood vessels. This is a process that we call angiogenesis. It is crucial to returning blood flow to the area for the delivery of oxygen and nutrients to the new tissue. HA's orchestrated role in this series of events all depends on the HA content being in proper balance. When it isn't properly regulated, the HA imbalance can contribute to conditions like chronic wounds. HA in the extracellular matrix is constantly being broken down by enzymes like MMPs. When the system becomes dysfunctional, too much breakdown of HA occurs. This results in a buildup of low molecular weight HA. Studies have shown that this excessive breakdown of HA contributes to the prolonged inflammatory stage that prevents the normal resolution of a wound, resulting in a wound that we would consider chronic. Given its integral role in wound repair, HA has been studied both academically and clinically to understand if and how we can harness the natural properties of HA to positively impact wound repair, degenerative joint conditions, and scar tissue formation. Hugh et al., shown here, has presented a good model of three-dimensional HA matrices reducing scar tissue formation and promoting tissue repair. Their study applied HA scaffolds with and without a cell population to full-thickness wounds in rats. Their results showed that wounds treated with the HA scaffolds closed almost 7 times faster and had significantly reduced scarring when compared to the control wound sites. The graph on the right shows that significantly less scar surface area was measured in wounds treated with HA constructs. An important observation of this study is that a cell population in the HA scaffolds did not make a significant difference compared to HA scaffolds alone. This observation points to the HA structure and signal being a key component in the mechanism that reduced scar tissue formation. Along with the Hugh et al. Study, publications and clinical trials investigating the impact of hyaluronic acid on wound repair and scar tissue formation have had a lot of success in positively affecting these processes. This field of study has grown into an industry that provides hyaluronic acid supplementation from a diverse range of sources. Hyaluronic acid is currently being sourced from Wharton's jelly of the umbilical cord, rooster comb, amniotic fluid, and from recombinant HA sourced from bacterial culture. Another rich source of hyaluronic acid is found in the amniotic membrane, where high concentrations can be found in the intermediate layer. Tissue and biomaterial engineering technology has formulated multiple delivery systems for hyaluronic acid. This includes studies that have created 3D scaffolds, hydrogels, and engineered membranes. These devices are often combined with other therapeutic components for more complex treatment strategies. In the last decade, the application of amniotic tissues has been more extensively studied clinically as they provide a unique and natural combination of regenerative components, which include native hyaluronic acid and a ready-made delivery system. Tissue engineering labs have focused on the potential of amniotic membrane for use as a wound covering. They cite the complex scaffold of collagen, proteoglycans, and glycosaminoglycans, like hyaluronic acid, that are found throughout the amnion, chorion, and intermediate layer. So, let's review. HA plays a critical role in maintaining and regulating tissues in the body. It naturally has beneficial characteristics that allow it to help regulate tissue hydration and make it the ideal biological lubricant. It also plays an important role in cell signaling, modulating inflammation, wound healing, and reducing scar tissue formation. It is important that the natural balance of HA synthesis and breakdown is maintained. When it isn't, it can contribute to dysfunction in the tissue repair process. HA is the subject of much academic and clinical research as a treatment option for chronic pathologies, and may be sourced from places like rooster comb and amniotic tissues. Thank you for listening. If you have any questions, please feel free to reach out on the stimlabs.com contact page. Make sure to look out for our next post about TIMPs and MMPs.